Hello students, welcome back to another video. Today we're going to be learning about nuclear physics. In yesterday's video we learned about the atom and the structure of the atom. We learned that in the nucleus, which is the center of the atom, there are protons and neutrons. Nuclear physics is going to be the study of what's going on inside of the nucleus between those protons, neutrons, and even within those protons and neutrons. Okay, here I've drawn my helium atom again, where I have my electrons on the outside, and then in the nucleus I have my protons and my neutrons. We can ask ourselves the question, what forces are keeping this nucleus together? So far we've only learned about two forces in this class. We've learned about gravity. The force of gravity occurs between masses. Usually it's more noticeable in very large masses. The magnitude of the force of gravity of something as small as a proton would be almost negligible, so we really don't even consider it whenever we're looking at things this small. However, gravity is much more significant than the other forces whenever the masses are humongous, like planets and black holes. The other force that we've learned about in this class is the electromagnetic force. The electromagnetic force occurs between charges, or moving charges for magnetism. More specifically, the electric force is between two charges, and the magnetic force is between two moving charges, but those two can be considered the same force, the electromagnetic force. This is the force that we utilize whenever we move things around. I utilize the electromagnetic force whenever I poke this marker and make it move. The electrons on my finger are repelling the electrons of the marker, so anything like that is just the electromagnetic force. Of course, we all experience gravity pulling us down to the earth, but there's two other forces that we haven't even learned about yet, and both of those forces occur within the nucleus of an atom. The first force that I'm going to introduce is the strong force. So this is the force that occurs between subatomic particles that are very close. In the case of the nucleus, the subatomic particles are the protons and the neutrons. These are very close together and they're held together by the strong force. You can think of the strong force as the glue which holds the atoms together. Really quickly, I just wanted to mention that also within the protons and neutrons that are inside the nucleus, there are even smaller subatomic particles called quarks. There are 6 different types of quarks, and different quarks and different combinations make different particles. I'm not going to get into too much detail of all that science, but 3 of these quarks together can make a proton or a neutron. And these quarks are also held together by the strong force. So not only does the strong force hold together the quarks within the protons and neutrons, it also holds the protons and neutrons together within the nucleus. We know that the electromagnetic force can't be responsible for keeping these things together, because protons have positive charges, neutrons have no charge, so there's no electric or magnetic force between those particles. There is an electromagnetic force between the protons and the electrons, and that's why the electrons stay close to the atom. But the strong force is what keeps the nucleus itself together. There's a lot more science and math to how the strong force works. I'm not going to get too into that to keep things simple, but now I'm going to get into the next force. This last force is called the weak force. It also occurs between subatomic particles, so within the nucleus of an atom, and the weak force is responsible for decaying the atom. Some atoms are more stable than others. The less stable ones are said to be radioactive because they experience the weak force more and they are decaying more rapidly than a more stable atom. In the last video we learned about isotopes. Isotopes are atoms that have a different number of neutrons than protons. Because of this imbalance, they are considered to be less stable or more radioactive. Isotopes tend to experience the weak force more rapidly and they decay. Whenever these atoms decay, they release energy as a result, which is the main theory behind nuclear energy, which we'll get into. Okay, so here's a list of the 4 forces that are known to man right now. I'm going to go ahead and start talking about nuclear energy and 2 different nuclear reactions that can occur. The 2 different nuclear reactions that can occur in an atom are fission and fusion. Fission is the process where the nucleus splits into 2 or more smaller nuclei, releasing a lot of energy. And once again, the weak force is what is responsible for the decay of these nuclei to split. But on nuclear power plants, they have fission reactors where this process occurs in a controlled way, and they use very radioactive substances that actively decay all the time. I think the most famous example would be uranium, but there are others as well. And this release of energy is harnessed at these power plants and can be converted into electric energy so that it can be used. This is also the basis of how nuclear bombs work. We all should know the history of the hydrogen bomb and how much energy is actually stored within the nucleus of an atom. The other nuclear reaction is fusion, which is when 2 or more atomic nuclei are combined to form 1 or more different atomic nuclei and subatomic particles. Humans already use fission all the time, but we have yet to create a fusion reactor This is a process that requires an extreme amount of energy. This magnitude of energy could be found in something like a star. So the sun, for example, has the energy capable of fusion reactions, which is the opposite of fission. Fission splits atoms, fusion combines atoms. I know there are a lot of scientists who are in the works of trying to find how to make a fusion reactor, but that hasn't happened yet. Maybe in our lifetimes we'll see a fusion reactor, although there are some scientists who are skeptical of its possibility. But anyways, these are the two nuclear reactions that can occur within the nucleus of an atom. Some applications of studying nuclear physics have led to some profound inventions and leaps forward, especially in medicine, where now we have radiation therapy, which is a huge resource to fighting cancer. We have diagnostic imaging, which is used all the time in the medical field to locate tumors and various injuries and illnesses. And of course, nuclear power is another source of energy that we have. Nuclear power is kind of a taboo topic, especially with all these old nuclear power plants blowing up and releasing all this radiation into the ocean. And that stuff is pretty terrible, but if it's done right with modern power plants, it can be done more safely and with less waste. So the nuclear power technology has a long way to go to make sure that no more catastrophes can occur. That's going to be all for today's video. Thank you. See you next time.